Afternoon, everybody. We have an interesting, fun AIME problem back in 2021, and let me just write down, just in case some of you guys have forgotten, if 14 is a root of this polynomial, that's the very same thing as saying 14 cubed plus a times 14. Okay, plus b is equal to 0. You know, sometimes modern day terminology, they call it a 0. A would be a 0. I mean, excuse me, 14 would be a 0. Okay, so they call it a root in the old days, but now they call this a 0 because when you put 14 in for x, put 14 here, put 14 here, you get 0. And similarly, it's specified that this other cubic expression has 3 as a root, okay? Now, both of these cubic expressions have a complex root in the form of m plus the square root of ni. Now, there's a result called, it's the complex conjugate theorem, I guess it's called the complex conjugate theorem. But if you have the plus version, that also implies that m minus, okay? M minus the square root of n I. And if you just think about the form of the quadratic equation, you can see why there's a plus or minus in the quadratic formula, but this is also a root, okay? Again, I think that's because any polynomial can be written as the product of irreducible quadratics and linears. Okay, I'm not quite sure how to prove that, but anyway, I believe that's the reason why this is true. Now that turns out to be quite important here because what I've done here is I've written down just a general form of a cubic. This is definitely a cubic. You have x times x times x with 3 roots, not necessarily distinct. Now if you expand this out, there's a lot of work going on right here to expand this out, but it's not hard to see that the sum of the roots minus the sum of the roots is the coefficient of x squared. Now that's where we get quite a bit of mileage right here, because notice back up here, there's actually a 0x squared term that's not present, but certainly you can think of that as occurring, right? There's a 0x squared term, right? So you see this statement down here, the 0 that you see right here is exactly because of this, right? Okay, there is a 0x squared term here, and we know that the sum, you can think of this as r sub 1 plus r sub 2 plus r sub 3, right? Okay, the sum of the, in other words, here's the coefficient of x squared right here, right? And it's the sum of the zeros, right? Minus the sum of the zeros. But it's equal to 0, so the minus sign doesn't really come into play. So that's where this statement comes from. And this leads to the fact that m is equal to -7. That's very easy to see. Notice how these two guys cancel in the summation. This term will cancel with this term. They're additive inverses. And you'll get that m is equal to -7. So you see we're halfway home, okay? M is equal to -7. This is sometimes called Vieta's formulas, folks, and this is why Vieta's is true. This whole setup here justifies something that's commonly called this Italian name, Vieta, okay? All right, now in a similar fashion, notice that the roots get multiplied in pairs is the coefficient of x, and that's just how this expansion goes. If you expand this out, you would see that this was true. I'm not going to show that work, it's way too tedious, but you see it's the product of pairs of zeros. All possible pairs of zeros products ends up being the coefficient of x. That's kind of that's what's going on with Vieta's. Vieta says the roots are expressible as coefficients of the polynomial. So for that reason, we get the very same sort of thing right here. You see, this would be like your R1. This would be R1. This would be R2 if you wanted to label them thusly. Okay, this would be R1, R2. You know, R1, R3 perhaps right here. Okay, and then what's the last one here? R2, R3, and again the order is not particularly important here. R2, R3, right? And again, notice that's the coefficient of x, but 18 is the coefficient of x. Isn't this cool, folks? So this 18 comes from this 18 right up here, right? All right, and again, once you do the arithmetic on this, now do note right here, one of the things that happened here, if a standard result here, if you have a plus bi, a plus bi, where I is the imaginary unit, I is equal to the square root of -1. And again, y'all, I think you all know, but I is equal to the square root of -1, which means I squared is -1. Okay? So a plus bi times a minus bi. Because of this unusual property of I squared being equal to -1, okay, this is just equal to, let me just write it directly above it. This is all equal to a squared plus b squared. Kind of ran out of room here. A squared plus b squared. A squared plus b squared by the difference of two squares formula is equal. Let me just put an equal there. Hopefully it's marginally readable, folks. And that's because I squared is equal to -1. Okay. All right. But anyway, that's how all this arithmetic occurs. You see how n just pops out of here because square root of n times square root of n is n, and two minus signs make it a plus, and so you get n is equal to 11. Okay. And so those are our two solutions, folks. M equals -7 and n equals to 11, and that means the original result here. What do we got here? This would be -7. You would have two different roots, right? You would have -7 plus the square root of 7i, and then, but we just found m and n. You could write out the form if you want to, but those are the answers. And hope you enjoyed that. I thought it was pretty cool. Liked it.